Hello everyone, and welcome to the fourth chapter of our Chemistry O-Level Lessons series. This chapter is called The Structure of the Atom, and here we have the learning objectives of this chapter. The specific topics of this chapter are listed in the description below, along with their chapters and timings. So, in this topic, you should be able to state the relative charges and appropriate relative masses of a proton, a neutron, and an electron. We are going to describe, with the aid of diagrams, the structure of an atom as containing protons and neutrons in the nucleus and electron arranged in shells. We're going to learn to define proton number and nucleon number of an element. We should be able to define isotopes, define relative atomic mass of an element, deduce the number of protons, neutrons, and electrons in the atom of an element, given the proton and the nucleon number of the element, example, carbon. State that the vertical columns of elements in the periodic table are called groups of elements and contain the same number of electrons in their outermost shell. These are valence electrons. And state that the horizontal rows of elements in the periodic table are called periods of elements and that the period number indicates the number of electron shells. So these were the learning objectives that we're going to complete in this chapter. So let's begin by first understanding the particles in an atom. So, all elements are made up of atoms. The atoms of one individual element are identical in every respect and differ from the atoms of all other elements. Atoms are made up of subatomic particles called protons, neutrons, and electrons. So, let's see what protons, neutrons, and electrons are. The mass of a proton is equal to the mass of a neutron. However, an electron's mass is only 1 of 1840, that of either a proton or neutron. So, even though the mass of a proton is equal to the mass of a neutron, the only difference between the two particles is that the proton is positively charged, whereas a neutron has no charge. It is neutral. An electron has a negative charge. So, together these particles make up a stable atom, a neutral atom, with the positive charge being cancelled with a negative charge as well. So, as the largest atoms still have less than 100 electrons, the electron's mass is regarded as so small it can be ignored. So, the protons and neutrons have equal mass, 1, and the electron's mass is only 1 of 840, that of either a proton or a neutron. So, the electron's mass is negligible. Here we have the symbols of these particles. The proton is represented with a P, with a small p, neutron with a small n, and electron with a small e. So now that we've understood the particles in an atom, the protons, neutrons, and electrons and their properties, we're going to move ahead onto understanding an element's identity. So, every element has its own proton number and nucleon number. We are representing the proton number by a capital Z and the nucleon number by a capital A at the moment. So, the proton number of an element is the number of protons in its atom, which is equal to the number of electrons. The nucleon number of an element is the total number of protons and neutrons in its atom. The nucleon number, not the neutron number. When we say the nucleon number, we are telling the sum of the proton and neutron number in the atom. The proton number is the number of protons in its atom, and this is equal to the number of electrons. So, the way we write atoms down is something like this, in which we write the proton number as well as the nucleon number. And using these two, we can identify the number of neutrons and electrons in this atom as well. So consider a sodium atom here, whose nucleon number is 23. Nucleon number means proton plus neutrons. This means its atoms contain in total 23 protons and neutrons. However, the proton number of sodium is 11. Here we write the proton number, which means it contains 11 protons and 11 electrons because the number of electrons is equal to the proton number. So if the proton number is 11, then the electron number would also be 11. And by this proton number, we can find out the neutron number as well. All we have to do is minus the proton number by the nucleon number and we'll get the answer. So by subtracting the proton number from the nucleon number, we obtain the number of neutrons present in the atoms. So from this we can deduce that a sodium atom has 11 protons, 11 electrons and 12 neutrons. You can see in a periodic table we have written elements like this. The atom symbol, like of sodium we have Na. For carbon we would have a capital C. So we write the symbol, we write the nucleon number on the left hand side of the symbol above the proton number. So here we have a table of the first 20 elements listed in the periodic table along with their numbers of neutrons, electrons and protons. So let's start. The first element of the periodic table is hydrogen. This has a proton number of 1 and a nucleon number of 1 as well. And so this would suggest that it has no neutrons, because when we minus 1 by 1 we get 0. So number of protons in hydrogen would be 1, number of electrons would be 1 as well, but the number of neutrons is 0. So hydrogen atoms are made of only 2 particles. Then we have helium, which has a proton number of 2 and a nucleon number of 4. And so when we minus 2 by 4 we get 2 again. So the helium atom has 2 protons, 2 electrons and 2 neutrons. Then we have lithium with a proton number of 3 and a nucleon number of 7. This would suggest 3 protons, 3 electrons and 4 neutrons. We minus 3 by 7. Beryllium has a proton number of 4 and a nucleon number of 9. So it has 4 protons, 4 electrons and 5 neutrons. Remember that the electron number is equal to the proton number. Boron has 5 protons, 5 electrons and 6 neutrons because it has the nucleon number of 11. Carbon has 6 protons, 6 electrons and the nucleon number is 12. So the number of neutrons would be 6. You can see the rest of the table and memorize the proton number and nucleon number of these elements. Now we're going to move ahead on to understanding what isotopes are. So isotopes, in simple words, are the atoms of the same element with different numbers of neutrons. So as isotopes have different numbers of neutrons, they have different masses. However, chemically they are identical as they contain the same number of electrons and protons. So remember, the proton number always represents the element of an atom. If the proton number is changed, the atom would be of a different element. So in isotopes, the proton number remains the same, but the neutron number changes. So if they do not have the same number of electrons and protons, then their proton number would change, and therefore so would the element. So here we can see that if the protons of a hydrogen atom change to 2, then it would no longer be a hydrogen atom. It would become a helium atom. So the proton number always represents the element, whereas the neutron number can change and form an isotope of the same element. So consider the element hydrogen. This can exist as 3 isotopes. First is the hydrogen, which is the normal one. The second is the deuterium, and the third is the tritium. So the difference between all of these atoms or isotopes is that they have a different number of neutrons. You can see the symbols of the 3 of these. They would be called hydrogen. They are represented by a capital H, as you can see. But the only difference between them is that the nucleon number is changing. Hydrogen has a nucleon number of 1, deuterium has a nucleon number of 2, and tritium has a nucleon number of 3. And so, when we minus the proton number by the nucleon number, we'll get the number of neutrons. The actual hydrogen atom has no neutrons, but the deuterium isotope has 1 neutron and the tritium isotope has 2 neutrons. So, the isotopic abundance of hydrogen is 99.985%, whereas of deuterium, it is 0.015%. The tritium is an artificial isotope. But now you can see the point. You can see this atomic structure of these 3 atoms as well. The hydrogen is a very simple one. It has 1 proton and 1 electron. The deuterium has 1 proton, 1 electron, and a neutron. And the tritium has 2 neutrons, 1 proton, and an electron. By artificial isotope, we mean the one which is man-made. So, the thing to remember about isotopes is that they are atoms of the same element but with a different number of neutrons. If the number of protons change, then they become an element of a different element. The proton number decides the element of the atom. If 1 changes into 3, it will not be a hydrogen atom, it will become a lithium atom. So, normal hydrogen gas is a mixture of these 3 different isotopes. Its atomic mass is the average of the nucleon numbers of hydrogen, deuterium, and tritium according to their isotopic abundance. This comes to 1.008, which is very close to 1 because of the high abundance of the hydrogen isotope. We say that 1.008 is the relative atomic mass of hydrogen. The relative atomic mass of an element is defined as the ratio of the average mass of an atom to 1/12 the mass of a carbon atom. Carbon-12 is chosen as the standard atom. Remember, carbon-12 is not an isotope, it is an actual atom. We call it carbon-12 so that we don't confuse it, but whenever we write down a number after an element like this, carbon-12, carbon-14 and stuff, we are representing its nucleon number. So when we say carbon-12, we should know that the actual carbon has 6 neutrons and 6 protons, a nucleon number of 12. So this is the actual carbon atom. But when we say carbon-14, then we should know that it is an isotope of the carbon atom. So for this, to recognize the isotopes and the actual atoms, you need to memorize their proton and nucleon number, the ones I've written in the table I showed before. So carbon is chosen as the standard atom because its mass of 12 units has been determined very accurately using modern instruments such as the mass spectrometer. So an element's relative atomic mass, this is represented as an AR. The R is in subscript. So the relative atomic mass of an element, not molecular mass, don't confuse it with that. We're going to see what a molecular mass is later on. But right now, the relative atomic mass of an element is defined as the ratio of the average mass of an atom to 1/12 the mass of a carbon atom. It's the ratio with the mass of a carbon atom. So the carbon-12 is chosen as the standard atom, which mass is used as a ratio with any other element to find that element's relative atomic mass. So we should remember this definition of the relative atomic mass. The relative atomic mass of an element is defined as the ratio of the average mass of an atom to 1/12 the mass of a carbon atom. So for example, natural chlorine exists in 2 isotopes. This is the chlorine-35 and the chlorine-37. The chlorine-35 is a stable isotope, the one which is written in the periodic table, and the chlorine-37 has a different neutron number. So an ordinary sample of chlorine contains approximately 75% chlorine-35 and 25% of chlorine-37. Therefore, the relative atomic mass is closer to 35 than 37. So what we're seeing here is that an ordinary sample of hydrogen or any other substance contains the actual atom as well as the isotopes of the atom. Like in chlorine, an ordinary sample of this chlorine would contain 75% 35 chlorine and 25% 37 chlorine. In the same way, normal hydrogen gas is a mixture of the 3 different isotopes, the hydrogen, deuterium, and tritium. And so its atomic mass is the average of the nucleon numbers of the hydrogen, deuterium, and tritium according to their isotopic abundance. So for hydrogen, this comes to 1.008, which is very close to 1. So we say that the atomic mass of the hydrogen is 1. In the same way, the relative atomic mass of chlorine would be closer to 35 than 37 because of the percentage of both atoms. Chlorine-35 is more than the chlorine-37. So here is how we can find the atomic mass of chlorine. So the mass number of chlorine-35 is 35 and the mass number of chlorine-37 is 37. Do not confuse the mass number with the atomic mass of an element. Okay? So the difference between them is that the atomic mass measures the total mass of an atom, whereas the mass number is the total number of protons and neutrons in an isotope. So, the mass number of chlorine-35 is 35 and the mass number of chlorine-37 is 37. The percentage is 75 and 25. So, we're going to be finding out the atomic mass of an ordinary sample of chlorine, which contains both the 37 isotope as well as the 35 isotope. So, the way we do this is we multiply the mass number of the first atom, which is 35, by 75 and divide by 100. 75 is the percentage of this atom. And then divided by 100 to remove this percentage. And we do the same thing with the other atom. Multiply the 37 with 25 and divide by 100. Then we add both of the values and what we get is 35.5. So the atomic mass of chlorine is 35.5. You can see this in the periodic table. The atomic mass, the relative atomic mass is given 35.5. The relative atomic mass of hydrogen is 1. Because 1.008 is very close to 1. We remove the points. So the natural element is made up of different isotopes of the atom. Like an ordinary sample of chlorine contains chlorine-35 as well as chlorine-37. And an ordinary sample of hydrogen has all the 3 isotopes with their percentages. And together all of these isotopes make their atomic mass. Make an atom's atomic mass. The relative atomic mass of an element is defined as the ratio of the average mass of an atom to 1/12 the mass of a carbon atom. So, here we have the similarities and differences between isotopes and atoms. The similarities are the number of protons. The proton number is always the same. If this changes, the entire element would change. So, isotopes are the atoms of the same element, but a different number of neutrons, and so this would be the difference between isotopes and atoms, the number of neutrons. Similarities are the number of electrons as well. The difference is the number of mass. The mass number changes because of the number of neutrons. The similarities are the proton numbers, which is the same as the number of protons, and the similarities are the chemical properties, but the difference are the physical properties, for example, rate of diffusion and density. So the physical properties are different from chemical properties. By chemical properties we mean the boiling point, the melting point, something like that. These are chemical properties. By physical properties we mean the density of the atom, the rate of diffusion of the atom, nothing involved with heating or cooling, nothing involved with temperature or anything like that, and nothing involved with the mixing with another atom and how it would react. Chemical properties also involve chemical reaction. How this atom would react with another atom. That would be another chemical property. Physical properties are simple, like the rate of diffusion, the density, the mass, the volume, and stuff. So the difference between isotopes and atoms is the physical properties, but the chemical properties are the same. That means that they behave the same. They have the same boiling point, the same melting point, and the same reactions with other atoms. So this was all about the relative atomic mass and isotopes. Isotopes are atoms of the same element but with a different neutron number. Isotopes are atoms of the same element with different numbers of neutrons. And the relative atomic mass of an element is defined as the ratio of the average mass of an atom to 1/12 the mass of a carbon atom. So now we're going to move ahead onto the arrangement of particles in an atom. How are these particles arranged in an atom? The protons, neutrons, and electrons. So the protons and neutrons are held tightly packed together in the center of the atom, which is called the nucleus. The number of particles in the nucleus, which are the protons and neutrons, is called the nucleon number, and this is equal to the mass number of the element. So the sum of the protons and neutrons in the nucleus of an atom is the nucleon number, and this is equal to the mass number of the element. Do not confuse the mass number with the atomic mass of an element. The mass number of an element is the number of the mass of the protons and neutrons in an atom, whereas the atomic mass is the mass of the entire atom. Okay? So the nucleon number is equal to the mass number of the element. This is written in the periodic table where each element has a nucleon number which is written above and a proton number which is written down. So the nucleon number, remember, is also the mass number of the element. So this is what we did here to find the atomic mass. We found the mass number of both the isotopes of chlorine and the percentages of them, and then did all this equation to find the atomic mass, not the mass number. This is the atomic mass. By the mass number, so the chlorine 35 had a mass number of 35, which meant that 35 is the number of neutrons and protons in the chlorine atom. And this chlorine atom had 37 nucleons. Mass number is 37, so that is the number of protons and neutrons in its atom. The atomic mass is completely different from the two. It is 35.5. So after adding the 35 to 37, we don't get a bigger number. We get 35.5 because this is the atomic mass, not the mass number. The mass number is the number of neutrons and protons in the atom. It's just as simple as a nucleon number. So the nucleon number is the same as the mass number. So the number of particles in the nucleus is called the nucleon number, and this is equal to the mass number of the element. So because the nucleus contains protons, it is the positively charged part of the atom. Because neutrons in the nucleus are neutral, they do not have any charge. But the protons have a charge which is positive, and so this part of the atom is the positive part of the atom. The size of a nucleus is very small in comparison with the overall size of the atom. So, for example, if we make a hydrogen atom the size of a football, then its nucleus would be the size of a pinhead. This is the size of a nucleus in an atom. So it's very, very small compared to the atom. Now, the electrons move around the nucleus like planets orbiting the sun. Have you ever seen the planets orbiting the sun? They have this circular path around the sun, which is the orbit, and they move in it. So, however, the electrons move rapidly and at relatively great distances from the tiny nucleus. You can see this over here. This is the model of an atom. And this is the copper atom. And you can see these are tiny electrons which are orbiting this nucleus. I mean, in this structure you can see that these orbits are very close to this nucleus, but in actual they are not. So the copper atom has 4 shells. These orbits that we are talking about are called shells. These are the tiny electrons that are orbiting it. The hydrogen atom is something like this. It has only 1 electron and 1 proton, no neutrons. So 1 shell in which this electron is orbiting it. So, electrons move rapidly and at relatively great distances from the tiny nucleus. So it is not possible to pinpoint the exact positions of the electrons within an orbit at any one time. However, each orbit does have a particular energy, okay? So we can say that these electrons occupy certain available energy levels. These energy levels are also referred to as shells. So, as I was saying before, we don't call them orbits, we call them shells. And these electrons obviously have some sort of energy that keeps them in these tiny orbits. So we call these energy levels shells. The orbits, we call them shells, which keep the electrons in their orbit, the energy levels. So each shell is capable of holding up to a certain number of electrons. The shells or energy levels are numbered from the nucleus outwards. So the first shell can hold up to 2 electrons. This shell is called a duplet. Then the second shell can hold up to 8 electrons, not 4, 8. This is called an octet. The third shell can hold up to 18 electrons. However, with the third shell, when 8 electrons are present, extra stability is gained. So the additional electrons go into the fourth shell before the third shell is completely filled. So the electrons in the outermost shell of an atom are called the valence electrons. These have great significance in determining the chemical properties of an atom. We shall see how these valence electrons help in bonding and determine how atoms join together afterwards in other chapters. So, The first shell can hold up to 2 electrons, this is a duplet. The second shell can hold up to 8 electrons, this is an octet. And the third shell can hold up to 18 electrons. But usually it doesn't get filled entirely to 18 because when it is filled with 8 electrons, extra stability is gained. So rather than getting filled with 18 electrons, the additional electrons go into the fourth shell before the third shell is completely filled. So remember, the proton is the positive part in the nucleus. The proton is a positive particle in the nucleus. The neutron is a neutral particle in the nucleus. Electrons are negative particles of negligible mass around the nucleus. The proton number is the number of protons in the nucleus. The valence electron is the electron in the outermost shell of the atom. The nucleon number is the number of protons and neutrons in a nucleus. So these are the different numbers of atoms and the different particles in the atoms. The three different particles, which are the proton, neutron, and electron. So in this table, we can see the electron configuration of the first 20 elements in the periodic table, and how these electrons are arranged around the nucleus are shown here. So let's first see the element table. We can see that hydrogen has 1 proton in its atom and 1 electron which orbits hydrogen in the first shell. Obviously, if there is 1 electron, it will be only in the first shell. Helium has 2 electrons and 2 protons, which are also in the first shell. Remember, we learned that the first shell can hold up to 2 electrons. This is a duplet. So helium has 2 electrons in the first shell. Then we have lithium, which has 3 electrons. As you can see, the atoms in the periodic table are arranged in the order of the number of electrons in the atom. We have lithium, which has 3 electrons, and so it has 2 in the first shell and 1 in the second, because the first shell can hold up to only 2 electrons. Then beryllium, boron, they keep on adding more electrons in the second shell till neon. Neon's second shell gets filled with 8 electrons, and the second shell can hold up to only 8 electrons because it is an octet. Then the sodium atom, 1 electron goes into the third shell. The sodium atom, which has 11 electrons, 2 in the first shell, 8 in the second, and 1 in the third. And then magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon, they keep on adding in the third shell. Magnesium has 2 in the third shell, silicon has 4 in the third shell, sulfur has 6 in the third shell, and in the end, argon has 8 electrons in the third shell, 8 electrons in the second shell, and 2 electrons in the first. So the third shell, even though can hold up to 18 electrons, it gets filled with only 8. And so the other electron goes to the fourth shell, as in potassium. In potassium, we have 19 electrons. So 2 in the first shell, 8 in the second shell, 8 in the third shell, and 1 in the fourth shell. That is how it goes on, till the fourth shell is also complete with 8 electrons, and the fifth shell starts to get filled. And that is the order of the atoms. The first shell can only hold up 2 electrons, and the other shells, all the other second, third, fourth, fifth, sixth, any shell can hold up to only 8 electrons. Now here you can see the arrangement of these electrons in the atoms. First we have hydrogen and helium, which has only 1 shell because they have only 1 or 2 electrons. Then we have lithium, which has 3 electrons, and so we have an octet, which contains 1. Beryllium has 2 in the octet, boron has 3 in the octet, and we go up to neon, which has 8 in the octet. 2 in the duplet and 8 in the octet. And sodium adds up another shell because it has 11 electrons. Then it goes on to argon, where this third shell also gets filled up with 8 electrons, and so the potassium gets a fourth shell. In the same way goes for the calcium and all the other elements, till this shell also get filled up with 8 electrons, after which a fifth shell would get added up. And then the sixth shell and the seventh shell. That is how atoms are made. That is the structure of the atom. So this is the electron arrangement of the first 20 elements in the periodic table. I hope you've understood these electrons, the shells of electrons, the positive, negative, and neutral parts of the atom, protons, neutrons, and electrons, and the arrangement of electrons, which shell holds up to how much electrons, and what are the names of these shells. We are going to move ahead now onto the periodic table. So this periodic table chapter would be covered in more detail. It has its own chapter, which we're going to understand in more detail, with a lot of different stuff and what the elements are in this. But here I'm going to point out the different things that we need to understand and remember about the periodic table. So let's start. First of all, the position of an element in the periodic table is determined by its proton number. Okay, so if the proton number is 1, like hydrogen has a proton number of 1, that is the first element of the periodic table. The second element of the periodic table is helium because it has a proton number of 2. As you can see, the electrons in this chart are also 1 of hydrogen and 2 of helium because the proton number is equal to the electron number, and this is the order in which the elements in the periodic table are arranged: 1, 2, 3, 4, 5, 6 in the order of the proton number, the increasing order of the proton number. So the position of an element in the periodic table is determined by its proton number. Then the periodic table reads like a book from left to right, and it is a list of elements in order of increasing proton number. Again, it's the same thing, except for that we have to read it from left to right. That is how the order of the proton number is increasing, from left to right. So let's look at the periodic table and how this looks like. So this here is the periodic table, and as you can see, it starts from left to right. So in the periodic table we have different segments which have different kinds of elements. Let's see. In the periodic table we have groups and periods. The vertical columns, these ones, are called the groups in the periodic table, and each element in the group contains the same number of valence electrons in its outermost shell. Okay, so group 1, every single element in this group 1 would contain 1 electron in its outermost shell. The horizontal rows in the periodic table, these horizontal rows, are called periods. So we have groups and periods. Groups are the vertical rows and periods are the horizontal rows, like this. So the period number indicates the number of electron shells. So all elements in the same period would have the same number of electron shells. And as we move across the period, it is gradually filled up with electrons. So this is period 1 with hydrogen and helium, and you know that helium and hydrogen have only 1 electron shell. The second period is this one. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, they all have only 2 shells of electrons because they're in the second period. The elements in the third period have 3 electrons, the fourth period have 4 electrons, and as we move across the period, like from lithium to beryllium, the shell gets filled up with more electrons. Of course, group 1 has 1 electron, 1 valence electron, group 2 has 2 valence electrons, group 3 has 3 valence electrons. Slowly these shells get filled up as we move across the free period. That's what I'm trying to say. So this is periods. The period number indicates the shell, electron shells, and the group number indicates the number of valence electrons in an atom. Okay, so now let me tell you the different parts of the periodic table. So this here is group 1, this section. As you can see, this is highlighted here. This entire section, this group 1, are the alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. These are the elements in this group. And this is the alkali metals. These are all alkali metals, okay? Then we have the second group, this one, which is the alkaline earth metals. These are called the alkaline earth metals. So as you can see, the first group and the second group are metals, alkali and alkaline earth metals. Then we have the transition metals, this entire block here. These two, as you can see, the lanthanum and actinium, they are part of this entire section. As you can see, their color also represents them. This is the transition elements. This is not a group, okay? This is not the third group. The third group is here, the one with boron at the top. This one is the third group. And then we have the fourth group, the carbon one, the fifth group with the nitrogen, oxygen, which is the sixth, the seventh one is with the fluorine at the top, and the last one is with the helium at the top, and this is the eighth group, which means that all the elements in this group would contain 8 electrons in their outermost shell. So we're going to see all of these elements and understand what they are in the other chapter, but right now I'm just dividing the entire periodic table for you to understand the different parts of it. This is the transition elements. Then we have the metalloids. Metalloids are the elements which are close to the staircase line. Now we're going to see these in more detail afterwards in the actual periodic table chapter, but let me give you an overview about what the staircase line is. As you can see in this periodic table, we can see this red staircase line. This is the staircase line which divides metals and non-metals, okay? So the elements beneath this staircase line are all metals, and those above the staircase line are non-metals, okay? But the elements close to the staircase line, either above the staircase line or below the staircase line, these are called metalloids, and they contain the properties of both metals and non-metals, okay? So this is the staircase line. So the elements below the staircase line are metals and those above are non-metals. These are the elements which are close to the staircase line and contain the properties of both metals and non-metals. So these are the metalloids, these are the non-metals, and these are the post-transition metals, which are metals basically. And these gray ones are the elements which are some new elements which have added in the periodic table. The properties of these elements are unknown, so that is why they are colored gray. But the last group, which is the eighth group of the periodic table, this is made up of the noble gases. This entire group, all the elements in this group are inert, which means that they are non-reactive. They do not react. The reason for this is because, first of all, this is the eighth group, which suggests that the valence electrons in the elements of this group are 8. They are complete. Helium has 2, neon probably has 8, argon also has 8, krypton as well 8, xenon, radon, they all have full outermost shells. That is the reason they are inert. They do not react because they have complete electrons. They don't need more electrons to keep them stable. We're going to see that afterwards, how these valence electrons are the reason why elements react with each other, the exchange of electrons. So these gases, they do not react. The last group, these are noble gases. Then this part of the periodic table, including these two are part of this section. This is this blue section, these are the lanthanides. Now this part of the entire periodic table is something that you don't really need to know. They have elements which are being produced by man, and there are some new elements which have been added in the periodic table. So the section that you have to know is this entire full section above. These are the artificial atoms, the artificial elements that scientists have been making. So this entire part, I hope you've understood it. We have group 1, group 2, which are the alkali metals and the alkaline earth metals, group 1 and group 2. Then we have the transition metals, and then we have the group 3, 4, 5, 6, 7 and 8. The 8th group are the noble gases. This part are the metalloids, this part are the non-metals, and this part are the metals. Again, these are some metals whose properties are not known yet because there are some new elements added in the periodic table. But now, here's what you have to remember. The horizontal rows in the periodic table are called periods, and the period number indicates the number of electron shells. So all elements in the same period would have the same number of electron shells. The vertical columns in the periodic table are called groups, and each element in the same group, contains the same number of valence electrons in its outermost shell. The group number is also determined by the number of these valence electrons. So, the position of an element in a periodic table is determined by its proton number. The periodic table reads like a book from left to right, and it is a list of elements in order of increasing proton number. The metals are found on the left-hand side of the table in group 1 and 2, the alkali metals and the alkaline earth metals. We've seen those. The non-metals are found on the right-hand side of the table and are those elements with 4 to 7 valence electrons. By 4 to 7 valence electrons, we mean the groups 4 and 7. Group 4 and group 7, these contain non-metals. Then the inert gases are those on the extreme right-hand side, group 8, remember, and are unreactive because they have 2 or 8 valence electrons in their outermost shell, which means that the outermost shell are full. They are full outermost shells, like helium. It has a full outermost shell. It is an octet and is completed with 2 electrons. And all the other elements in this group have 8 valence electrons, which means that their outermost shells are also complete. So they are inert. They do not react. They are unreactive. They do not have to react with any other element, because usually the reason why elements react is because they have 1 electron less or 1 electron more, or 2 electrons less or 2 electrons. They always fight for a complete outermost shell. Like sulfur, it doesn't have a complete outermost shell. It has 6 electrons in its outermost shell. So it will try to bond with another atom that could give it 2 electrons. And obviously that atom would also take something from sulfur. So that is how these elements actually react. That is the reason why they bond, they react with other atoms, because they want their outermost shells to be complete. And the elements in the 8th group, they have full outermost shells. So they do not have to react with anyone because their outermost shells are already complete. So that is why these gases are called inert. And remember, these are gases. I forgot to say this. These are not metals, these are gases. Inert gases. So this was all about the periodic table. The vertical columns in the periodic table are called groups. The horizontal rows in the periodic table are called periods. So this was it for today's chapter. It was a very fun chapter, as you can see. And in this chapter, we've learned about the particles in an atom, protons, neutrons, and electrons. What are the weights and the symbols and the charges of these little particles? How these particles tell the element's identity. What is the proton number? What is the nucleon number? And how these numbers give an element's identity. The table, here is the table in which we have the first 20 elements of the periodic table along with their proton, nucleon, electron, and neutron numbers. Then we understood what isotopes are and the atomic mass. How we find the atomic mass of an element, and what is the mass number, the difference between the mass number and the atomic mass, the similarities and differences between isotopes and elements, and how particles are arranged in an atom. The nucleus of the atom, which contains the protons and neutrons, and the different electron shells, which we were calling orbits, the different electron shells in which electrons orbit the nucleus, the duplet, the octet, and the last electron shell, in which we have valence electrons, which are the electrons in the outermost shell, and how much electrons can each shell hold. We saw the electron configuration of the first 20 elements of the periodic table, the order in which the electrons build up in the atoms. Then we saw the periodic table, the position of elements in the periodic table, the groups and periods, and we understood what the period number and the group number indicate, the different parts of the periodic table, different groups of the periodic table, the alkali metals, the alkaline earth metals, the inert gases, non-metals and metals. So this was it for today's chapter, the structure of the atom. I hope you've understood the structure of the atom and all the different things I've explained in this chapter. We have successfully completed all the learning objectives in this chapter that we read in this beginning. The next chapter is going to be elements, compounds, and mixtures. So thanks for watching, and I'll see you in the next video.